Hello, today we are going to look at what would be a review of thermochemistry. It still should be something of a review. So let's go. All right, thermochemistry. You guys did this last year in the spring with distance learning. So again, it should be somewhat of a review, not brand spanking new. A couple definitions to look at first. Energy, the capacity to do work or produce heat. Looking specifically at heat when we go through this. Potential energy, things we should already know. Energy due to position or composition. And then kinetic energy, kind of big focus of thermochemistry, energy moving around, deals with this equation. You should know this equation and how the variables relate to each other. Kinetic energy, 1/2 mass times velocity squared. How any change in mass, how that affects the energy, or change in velocity, how that will affect it. So a big thing this year with equations is we really need to focus on how the variables affect one another, which is going to be the biggest help and support to what we're doing. We know energy can be kinetic. Thermal energy is what we're focusing on in this chapter, or the next actually two chapters, thermochem and thermodynamics. So just giving you an idea of what's going on. That middle picture having to do with work. The topic of work is not part of the class, so don't worry about it. All we're going to be focusing on is kinetic energy, thermal energy, things of that nature. Little flow chart just to kind of see what's going on. So ultimately, we're looking at potential energy, usually contained in bonds. So bond energy, breaking and forming bonds. Kinetic energy, gases, things moving around, obviously. So just to kind of see what's going on. We've seen potential energy. The goal here, again, is just to review, make sure that we know what is happening, what's going on with these different aspects of energy. Potential energy, again, based on where it's located. So the higher you are above the ground, the more potential energy. As it begins to fall, converts into kinetic energy. Electrical energy, we'll see that when we get to electrochem at the end of the year, or end of the AP Chem before the test. Heat or thermal energy, our goal right now. Light or radiant energy, nuclear energy, chemical energy, so reactions and stuff. So many forms of energy which we are all aware of at this point, but still have an idea of, should know what's going on. Conservation of energy, you guys have heard this, you know the law of conservation of energy, similar to the law of conservation of mass. So nothing new here. First law of thermodynamics, total energy content of the universe is constant, never changes. We know this. We also know that energy can only be transferred or converted between different forms of energy, but total amount of energy must be the same at beginning and the end. So a little diagram, push on a spring, mechanical energy, which is also kind of doing a little bit of work, which we don't really worry about in that sense. But, the mechanical energy being stored in the spring, we release it, turns into kinetic energy. We didn't lose energy, we didn't gain energy, it just got transferred into the object. So, first law of thermodynamics, again, a review, excuse me, thermodynamics, the study of energy and its, interconversions. Sorry about that. So again, review-ish. So it's interesting, you can never design a system that will continue to produce energy without some source of energy. It's got to come from somewhere, and it's got to go somewhere or be stored and then used later. But you can't just make it up out of the blue from nothing. All right, state functions. it's a big aspect of thermochemistry and this class. The big thing about state functions, it depends only on the present state of the system, how it started, how it ended. It does not matter how it got there. So you look at something at the beginning, you look at it at the end, everything in the middle, we don't care about yet. That's going to be a later topic. Energy is a state function, the concept of energy. So, person standing at the top of Mount Everest has the same potential energy whether they hiked up there or got into a plane and then skydived. So, if you think about it, both people started on the ground, and then one took forever and hiked to the top of Mount Everest. Their starting was the ground, and their ending was the top of Mount Everest, 28,028 feet, so to speak. But then the guy, same person, or different person, sorry, got into a plane, flew up higher than Mount Everest, jumped out of the plane with a parachute, and came down to the same location as the one who hiked. The beginning and the ending positions are identical, but they took two completely different ways of getting there. So all we care about in a state function is beginning of end, not the path or the process to get there. Work, however, is not a state function. Work, for example, is you getting up from your desk at school and lifting up your backpack. You're applying a force, the lifting of the backpack, through a distance from the floor to your shoulder. That's looking at the distance traveled. That's why work is not a state function. Another example of it has to do with, again, going up a mountain. One person goes up the side of the mountain and one person does a bunch of cutbacks and zigzags. Either way, they start at 0 and they end at the top of 10,000 feet, according to the image. One took over twice as amount the distance to get there, but the beginning and the end are the same. All right. Energy change in chemical processes. We should have heard these terms or seen them: endothermic and exothermic. Endothermic energy is going into the system, like endocytosis. For those of you biology majors, remember things going into the cell. So when we look at system versus the surroundings, the system is always the reaction itself, and the surroundings is everything else. So in an endothermic process, the system is gaining the energy, the surroundings is losing the energy. So that negative sign means a loss of energy. You can't have negative energy. You're not pissed off or anything. But the negative energy, the negative sign represents the direction of flow. The positive sign, same thing, the direction of flow. Exothermic, obviously the opposite, so energy flows out of the system. So you biology majors, exocytosis, the cell is giving something up. Notice the algebraic signs have switched. It's the exact same system, but the energy is going in a different direction. Or any system for that matter. All you need to know is the direction of energy flow. When you are talking about energy, because there's both a positive and negative value in your answers, you need to, numerical answers, sorry, you need to make sure you include the positive or negative. If it is a positive answer, you still include the positive. If it's a negative answer, you have to have the negative sign. You cannot just say negative X joules is released. You have to have the negative sign. You do not have to have the word released, but the word released does not replace the negative. Every single answer dealing with energy must have both positive and negative. All right, system and surroundings. Again, already kind of talked about that. System is what you're looking at, the reaction itself, the process. The surroundings is everything else. And our goal is to kind of figure out is what's going on, what's the direction of energy flow, what's happening when it goes into the system, or what's happening when it leaves the system. Our potential energy graphs from an endothermic process, notice that the products are of higher energy than the reactants, so we have a positive delta H. Change in heat is what H represents. From an exothermic process, oh lovely, it's out in the way. It's the opposite. The products have lower energy than the reactants do from beginning to end, so it represents a negative value or energy being released in the process. You should be able to identify either of these graphs and be able to draw either of these graphs and label things and identify different parts of it. All right, calorimetry, the amount of heat absorbed or released during a physical or chemical change that can be measured. We saw this in the spring. So when you put two objects together, heat has to be exchanged. It has to flow. Usually by a change in temperature of unknown quantity of water. So something happens with water and we can measure the water increasing its temperature, or maybe the water is decreasing its temperature. Either way, we cannot put a thermometer on the reaction itself. There is no way to measure heat being lost or heat being absorbed by the actual system. But the water being known, we can measure it being the surroundings. So if water gains energy, what happens to its temperature? Hopefully you said that the temperature goes up. So if water is gaining energy, then the system is losing energy. So the process is exothermic, and vice versa. Our relationship, calorie, and specific heat. So 1 calorie is the heat required to raise the temperature of 1 gram of water by 1 degree. Calorie you guys are used to, obviously eating, things of that nature. In chemistry, people do deal with calories, but we also deal with specific heat. They represent the same thing, just kind of a different wording to describe it. BTU, British Thermal Units. Just so you know, the standard system, not the metric system. Specific heat and calorie are more metric, but BTU. So if you buy like a space heater for under your desk or in the garage, or you're buying a barbecue and it talks about BTUs, how much does it give off? That's where it's coming from. Energy, we deal with joules of energy. Your house does kilowatt hours, which we don't really care about. We're not using that one. But ultimately, its energy comes from looking at mass in kilograms and velocity is meters per second squared. So you put it all together and you get the joule of energy. So everything we deal with joules or kilojoules. It's just a metric system, which you guys are aware of. So that's where it kind of the joule comes from. It's a derived unit made up of multiple different measurements. This comes in handy later on in the year. Not that you're solving for meters per second or kilogram, but it's just making sure you understand the relationship where it comes from. All right, a bomb calorimeter, really cool thing to use. Obviously, we don't have it in high school. When you guys get to college, you'll be able to probably use one. In my college, we showed up to my physical chemistry lab, and the professor was like, yeah, I forgot a bunch of stuff. Gave us all a couple bucks, go to the vending machine and grab random stuff. So we got different potato chips, we got different candy bars. Basically, you take a piece of a candy bar. Let's take like a Three Musketeers bar, took the inside of it, stuck it in there where the sample is. You have a known amount of water. You have the initial temperature. and you basically ignite the food and blow it up. Little explosion inside that little vessel. Well, the energy given off by the explosion is absorbed into the water. So if I know how much energy is absorbed, that theoretically should equal how much energy was given off. Therefore, I can find out how much energy was in that sample of food or whatever you did, or whatever you used to test. So again, finding change in energy, we keep everything constant, gets rid of variables. The other thing you have to be aware of is heat capacity. So the bomb calorimeter itself, the actual material, is going to absorb some of that energy. So energy from the explosion goes to both the water as well as the bomb calorimeter itself. So two things are absorbing some of the energy. The heat capacity, as you can see, units of kilojoules per degree, has no reference to the mass. Mass is irrelevant in heat capacity. So you have to do a couple calculations when you're trying to figure out total amount of energy. But for our purposes, not this year, we use the coffee cup calorimeter. Pretty straightforward, does the exact same thing. The coffee cup calorimeter also has a heat capacity. So when a reaction occurs inside of a coffee cup, the water itself absorbs the energy, but so does the styrofoam cup. So there's kind of two calculations that have to occur. Here's some different heat capacities of different objects, which also kind of supports why certain things are the way they are. Take a moment and look at copper. Copper's got a pretty small number. Think about the plumbing that is inside of your house. Copper tubing is used for most of the plumbing. So when your hot water heater heats up water for you to take a shower, the water has to travel from the water heater all the way to your shower and hopefully stay hot. Well, it's a very small number, so not much energy is absorbed from the copper tubing. The water then stays hot. By the way, look at the value of water compared to that of copper. Pretty big difference. You're like, oh, why not just use lead? Think about that one. You really want lead in your water that you're taking a shower with? That wouldn't really work too well. Gold would obviously be way too expensive. Iron tends to be too heavy. And copper is a better material to use. Another interesting to look at with these two things is aluminum. If you guys are into cooking or baking with aluminum, you can bake something in an oven at 400 degrees for 5 hours. You pull it out of the oven, almost instantaneously, you can touch the aluminum and remove it, and you won't burn yourself. When I reheat pizza for my kids the next day, I'll put the broiler on in the oven, which is 500 degrees, and I'll just put it in there for, 5-6 minutes, melt the cheese again, get it all nice and toasty. I can reach into a broiler, bare hands, grab the foil, and take it out. It has such a small number, it absorbs very little amount of energy over time. If you try to heat water up to make pasta, it's going to take a while to heat it up. We've all probably experienced that. Interestingly, if you take a boiling pot of water off the oven or stove and you put it on your counter, it'll take even longer for it to go back to room temperature because the value is so high. If you've ever been to a sporting event, usually in the wintertime, high school soccer, best thing to do is you sell baked potatoes. Well, when you sell baked potatoes, what do you wrap them in? That's right, aluminum foil. Wrapping them in aluminum foil, when you take them out of the oven, after being in there for 350 degrees for an hour and a half or so, they will stay hotter longer because it's a very small number. So all the materials you guys use in cooking, as well as plumbing and things of that nature, are chosen partly because of its specific heat value. So again, specific heat measures the substance's intrinsic ability to absorb heat. Smaller the number, absorbs faster, but it's smaller packets. Whereas larger the number, takes longer. That's why it takes a while to heat water to boiling. So by definition, amount of heat required to raise the temperature of 1 gram of 1 degree, which is also a calorie. We use the capital letter C for specific heat. Units are joules per gram degree Celsius, so there's a gram part of it. Keep in mind, specific heat capacity is different than heat capacity. Both have a letter C. One has a mass unit, one does not. Specific heat capacity has that mass. Molar heat capacity is the exact same thing as specific heat capacity. It's just instead of a mass unit, it's per mole. And we guys already know what mole is. So here's a little question for you. Maybe pause the video, or let's look at it for a second. So make a note of your answer, write it down on the side of a piece of paper, and then move on to the next one. And here's the answer. Okay, so 3 different metals of the exact same size, so mass goes out the door. They're all at 25 degrees, and we're going to add identical amounts of heat. Copper, having a larger number, is going to absorb more energy in order to increase the temperature. So if they all get the same amount of energy, copper absorbs more, its temperature is going to go up the most from 25 degrees. All right, calculations, pretty straightforward. Q equals MCAT. So the left equation is the one I always start with, and then obviously you can rearrange your variables in order to get the variable that you're solving for. Lowercase q is heat. Keep that in mind. Capital Q, something else. Sometimes they're not really interchangeable, but when it's dealing with heat, it's usually helpful to use lowercase q, but sometimes you come across capital Q. It happens. So, looking at the idea of thermal energy transferring, we have a block of metal at 55 degrees is added to water at 25 degrees. Thermal energy transfers from the metal to the water. What is the direction of heat flow? It's not up or down, it's not left or right, it's not zigzag. It is hot to cold. Heat always goes from hot to cold. So metal at 55, water at 25. Clearly the metal is higher temperature, so energy has to go from the hotter object to the colder object. To figure out the exact temperature change, like what's going to happen, we got to know the mass of the metal, mass of the water, specific heat capacities of both. So we get this equation where Q metal equals Q of the water. Little mistake there. The negative sign should be on the metal. I copied this from another place to put the image in. So at the end of the day, mathematically, it doesn't matter where your negative sign is, but conceptually, the negative sign should be on the hotter object. But I apologize for it not matching here. But, we have the mass. We'll have to get the mass of each. We'll have to get the specific heat of each, and then figure out delta T. So let's see what happens. Here's a problem. You can press pause. Alrighty then. So using the equation we just saw, Q equals a negative Q. Put your negative sign on the correct side, the hotter object. You have MCAT equals a negative MCAT. Put all variables in that you know, and then solve for the unknown. And here's what you should get. So negative Q went on the side with the iron, because it is, if the iron is decreasing by 10 degrees, it's losing energy. Therefore, you know the negative sign goes there. I know the mass of iron. I know the specific heat of iron. I know the temperature change of iron. I know the mass of water. I know the specific heat of water, but I don't know the temperature change of the water. Plug everything in and solve. All right. Next one. You can pause the video. So again, you have MCAT equals a negative MCAT, because Q equals a negative Q. Plug all your data in that you know. Since you're solving for the final temperature, they both have to have the same final temperature at thermal equilibrium. We go to plug everything in. Since it's water on both sides, on the third line, I just did not include the specific heat because it's the same thing on both sides. So I just didn't use them. And then you solve for it and you get your answer. And that is it for our review. Thank you very much.